taking a look at the concept of conservation of charge through the lens of the question, what makes charges move or stop moving? Now, at the end of the last video, I left you with this challenge where we had two metal spheres that were connected by a conducting material, so like a wire, and one of those spheres had an excess of 60 electrons, and one of those spheres had a deficiency of 60 electrons. And we were going to try to take a look to see what would happen when these two are connected. Excuse me. So here we go. We're going to take a look at this. I'm going to make each of these six electrons that I draw here. We'll kind of do it like this. Represent 10 of the total, right? And then over here, like we said before, I have 6 holes. So I would have 6 little holes. So here I have an excess, and here I have a deficiency. Now, what we're going to do here is actually zoom in a little bit on the object. So I'll zoom in here, I'll draw a larger version of this, and we're going to take a look at this object over here with the 6 electrons, so therefore each making a total of negative 60, and we're going to see that according to Coulomb's law, the farthest distance between them is the best configuration, or the configuration that needs the least amount of force to hold them in such a way. So we know that in terms of energy, it's always better to be at a more equilibrant state, so a state that requires less energy to be in. So it would imply that this is the best solution. So when you have a metal object, the charges will always distribute evenly along the surface of that object, provided that that object is uniform, which for right now it is. Now, since we're doing this learning in the time of COVID, what we're going to say is use an analogy to see what might happen, and you can use this to determine any situation. So let's say that these 6 electrons are 6 people, and one of them is positive for COVID, but we don't know which person it is. So they're always going to stay as far apart from each other as possible, which happens to be this configuration. Now, if we come back to the original picture again, and I connect the wire, that's like opening a door and allowing a passageway to another room, what we'll see here is that it depends on whether this other room has a deficiency of electrons or just a different number of excess electrons, which we'll look at in a second. So what's going to happen is, because these are all individual little holes, little rooms where they can shut the door and they can leave, they will each take one of those rooms and fill those up, leaving no excess here and no deficiency here. Now, a way that we can show this through conservation of charge is that we can basically say that charges are not deleted or don't disappear or are destroyed. They just are moved from one place to another. So I'm going to show this mathematically, and what I'm going to say is that the charge, the final charge on either of the two, because this will be the same after the conduction occurs, will be equal to the charge on number 1 plus the charge on number 2, so that's the total charge in the system, evenly distributed between the two, so divided by 2. And we need to keep in mind that the sign matters, as we'll see in our next example. So if I showed this here, now I'm not actually writing the charge, I'm just writing it as the product of the number of electrons and E, just to save time. So I put these two together, divide by 2, and I clearly see that there is a 0 net charge on either one of these after this has occurred. Now let's move to a scenario where we might have something that's fairly similar, So they're set up in the same way, except this time what I'm going to do is I'm rather going to say that this one, let's leave this one with the same negative um, 60 here, so that's going to be an excess. And I'm going to say that this one has an excess as well. And the excess here, I'm going to say, is just an excess of 30 electrons. So what I'm going to do is connect the two. And if I think about it in terms of the idea of COVID, like we just did before, let's do our representation where we have 60 or 6 representational electrons, which I've drawn 7 there, sorry. And over here I have just 30, right? So 1, 2, 3. So we can see that total between the two, if I add these two together, I have negative 60 plus negative 30, and it's clear that there are 90 excess electrons between the two in the entire system. And so if I'm trying to calculate what the final charge on each one would be, it's very clear that I would take that, divide it by 2, and I would end up with negative 45e, meaning I have an excess of 45 electrons on each of the two spheres at the end, because that would be the configuration where they're the farthest away from each other as possible. Now, so far, what we've been looking at is a scenario where the radius here and the radius here are equal. But this might not always be the case. And so what we're going to look at here, what I'm going to leave you with, is a challenge. And this is the challenge. The challenge will be that I have a sphere. Let me put a sphere in here for you. And this sphere has a counterpart that is 4 times smaller, or its radius is 4 times smaller than the other one. So I'll go ahead and write this in. And we can say that R1 is equal to 4 times R2. Now let's say that I connect the two. How will the charges distribute between them? Will it be the same even distribution like we've been saying in this idea of conservation of total charge? Or will there be a difference because of the size of the charge? Try to figure that out. And in the next video, we'll come together again and we'll try to see if we can figure it out together.